Okay, cool. We can go ahead and get started. Thanks everybody for joining ML Performance Reading Group. Today, Kunjan, aka Cool KP, is presenting, so I will hand it over to you.
All right, thank you for that intro. Um, yeah, hi guys. We're today gonna discuss USP, which stands for Unified Sequence Parallelism. It's a sharding strategy in context of long sequences. Um, the rough gist of it is that it combines. It's a hybrid 2D parallelism strategy combining deep speed Ulysses, which is a sequence parallelism strategy, and also ring attention, which is also another strategy. But both have different behaviors within the attention op, which is going to be the main focus of this optimization. Um, in case anyone is not familiar with I think everyone should be familiar with ring attention. We had a session in this reading group before, uh, presented by Daniel, on ring attention. But uh, I can quickly cover both of these things at a high level. So this is Deep Speed Ulysses, which is Microsoft made this paper. They build on top of Megatron. And the idea here is that instead of this paper compares with sequence parallelism that was done in Megatron alone, and the idea is instead of having an all gather of KV, um, when you have sequence sharded in the attention op, here they propose an all to all, and in which reduces which gathers on the sequence dimension for entering the attention op, and then scatters on the head dimension. So basically, the computation, you don't you're substituting the all gathers with the all to all and a reduced gather. Yeah, with two all to alls. You're substituting the all gather and the reduced gather with an all to alls on for the output and for the input. That's the gist of this. But the key point here to note is that the attention during the attention op, we're shadowed on heads. Uh, any questions? And this is, I think, is fairly straightforward. Right. So the reason that I'm explaining this and emphasizing the local dimension is because it will be useful to keep that in mind when we go through the unified sequence parallelism algorithm, which basically treats this does performs this strategy outer dimension of the mesh. So yeah, that's why I emphasize this. So the first step we will see in the algorithm will be to follow this algorithm. And in ring attention, oh wait, this isn't ring attention. This is ring attention. Yeah, and in ring attention, I think we have seen that we do an online softmax, and we arrange the devices in a ring where each device computes a partial numerator and denominator of the attention up, and then for a partial sequence, and then passes it on. Uh, and at each level, we perform a correction of the row-wise softmax, row-wise max softmax, and then uh, recorrect the numerator denominator, keep and passing it on. Um, and we have a number of devices times this rotation, which will give us the final output. But in this, the local dimension on each device is shaded by sequence. So if you have so we are shaded, the QKV on each device is shaded by sequence. This is the difference between this and the deep speed Ulysses, where we were shaded on heads. So, uh, and another key point here is that these producers, prior to entering the attention op, we were shattered on sequence, and then we did an all to all. which was a gather sequence, and scatter on heads. So that all to all is not needed here in because we stay sharded on sequence within the attention op, and we instead hide the communication in the ring by with these partial computations of the numerator and the denominator. Uh, yeah, idea is to kick off the comps. I think if you look at Daniel's paper video on this, it will be better explained where he explained about you have to allocate buffers and how the algorithm actually is implemented. Uh, Anybody have any questions so far?
Can we go back to the Ulysses really
Yeah.
quick? I have kind of some questions. So I'm not as familiar with this, but I get the gist of it. Like rather than sharding along the sequence dimension, and so each device will have a chunk of the sequence dimension, and for that chunk, we'll have every head. Instead, they do this all to all, and now we have, we're sharded along the head dimension, and so for like say one device will have responsible will have like one head, but it'll have the full sequence dimension.
Yeah.
Um, but
They
like
will have the ones. You said
so
they will have the full ones.
yeah, it'll have the full sequence. And so in the paper today, they just briefly mentioned, oh, cool, you can use since you have the full sequence, you can just use a regular flash attention kernel, basically, which is cool. Like that's convenient. But like, what is the actual performance benefit? Is this like, did they have any numbers or anything that shows like it's like a memory optimization, or is it
What,
like a comms optimization?
you mean for Ulysses?
Yeah.
Yeah. That's a good point, actually. I did highlight this. So that they're saying the main benefit is on the comps, right?
Mm-hmm.
Because they're saying it's better, it scales better uh, versus two all gathers. That's what they're saying.
Mm-hmm. How does it affect
So
your peak memory though, does it say? Because if you have the full sequence dimension, even with one head, like what if your sequence is like 1 million or 10 million?
yes, exactly. Yeah, exactly. That is the drawback of this actually, where
Mm-hmm.
it doesn't solve the problem where of HBM. Like if your sequence length is huge, you are
Mm-hmm.
you're still you can run you have you can have out of memory because you didn't shard your sequence length. Like a lot of
Mm-hmm.
times people fall consider sequence parallelism in practice because of this memory issue and to begin with. So
And that's
yeah,
why they're
that is
combining with ring attention, which does shard along sequence for the in that. Well, I won't get ahead of ourselves here. I'll let you keep going.
yeah. But you bring up a good point here. Actually, we can. I would like to get the thoughts of you and others here about this statement that this says. So as I mentioned, we perform an all to all. So you would do an all to all. You have an aggregate message size of 3 NH, which is basically for the QKV. So you to go from sequence to head sharding. That's what they're saying. And then, but this is what they're saying. Note that this communication volume is constant when both N and P are increased proportionally. I don't get how this is like a. I mean, I don't know how to say it. Like, I don't know how this is a point that makes this a, a great algorithm. Like, I don't know how this is a point in favor of it of this. Like, isn't
Um,
this
I don't know. Let me
aren't
read
they
this
just
really quick.
I think what they're saying here is that that with higher degree of parallelism you don't have a higher increase in an increase in a communication volume. That's what they mean. That's the advantage of the all versus the all gather, where if you have higher degree of parallelism you will have higher communication volume.
Okay, so sequence length is N and P. Okay, so um, yeah, it seems like just they're basically just saying with the two alt-alls here, their scalability has a complexity of O of n over p for com scalability as O of n over p asymptotically, and so as long as you increase both, it's scalable essentially. It's not going
Yeah,
to increase like super linearly.
yeah, it's
Um,
going to increase linearly. That's
yeah,
what they're saying.
yeah.
Yeah. And then they're saying that they're claiming that this is better than the all gather where it doesn't increase linearly.
Oh,
because the
really? Let
P
me
is
see.
therefore the Megatron sequence parallelism incurs a communication volume per link of 4 nh, which is P times larger than that of deep speed. So
I
they're saying
see.
if you that's the point they're making. But I think that is just because the yeah because of the I don't think people implement Megatron LM like that. The implementation that they're referring to.
Hmm.
Yeah, where basically in this Megatron LM, the inside the attention knob there is no sharding. That's why they're saying this.
Well,
It's not
oh,
sharded
so
on.
is that why they're not dividing by P for the?
Yeah. It's not even sharded by head. That's why they're not dividing by P.
Isn't that
So
kind
the
of a weak baseline then? I guess they're just comparing it to,
yeah,
yeah.
yeah. I think it's
Uh,
like a you compare against the weakest to make yourself. Yeah, I don't. Yeah. That's what I was a little bit puzzled that why was this even mentioned in this? Yeah.
I don't know. Did you
But
check with? Did you say the authors work? Like you know them, or did you
no,
check with
no,
them?
I don't know. I don't know these
Oh,
authors. I don't know these authors. Yeah, I talked to the we can. I talked to Half, who is the Ring Attention author.
oh, cool.
Uh, yeah. I discussed with him about the USB. I can summarize his thoughts at the end of when I introduce USP to everybody here.
Oh, well, I guess we can.
Yeah. I guess anybody have any? I hope you're familiar with ring attention. I think it would be if you're not, it's better to just ask a clarifying question because it's pretty important to understand what ring attention brings to the table in terms of hiding comps as well as memory reduction, activation memory reduction. Um,
Um, so just have one question regarding ring attention that in attention and the async TP thing, we are overlapping communication and repetition, but I think there's even a newer way of doing the communication in NCCL, which is even better than ring attention. I'm wondering if
use
you
which one is better? So I didn't get catch your last point.
think the nickel people, they somehow modified the communication primitive such that you don't even need ring attention and it's like handled the communication layer or something. I don't know. Like I'm just wondering, are you aware of that? Like I heard that in a nickel video and a DTC video, but I cannot find it. That's what I was
I
wondering.
see. I I don't work on GPUs uh, and PyTorch. I'm
Ah,
mostly work on TPU
I'm
and
not
jacks.
familiar
okay.
with that either. I'm also unclear why, if they just have a more, I guess you're just saying
But
there's a more efficient nickel comms primitives that make the comms overhead like
yeah,
less impactful, so you don't need ring attention. I wasn't quite clear on your point.
y- yeah,
Mm, I think
I
they did ring attention at the level of nickel and they improved the communication primitives. Like the number of user buffers that you need to use for the primitives, those are reduced.
I
They
don't
were saying
understand
that
that
it's even
sentence. Like,
better
doesn't
now.
make sense to me. They did ring attention at the level of nickel. Like, I don't. Can you rephrase
Hmm?
that? Because nickel's just like it just provides like all gather, reduce, scatter, etc. Like,
I don't know
Yeah,
if
yeah.
I
I can maybe ping in the channel after the call. Yeah,
yeah, that'd be helpful.
yeah.
I can say I mean I do want to clarify that like the async TP and SP blog, the very good blog that Daniel wrote here is not exactly it's not the same sharding strategy as ring attention. Uh, it's sharded on heads within the attention app.
Hmm.
So this is a kind of a different strategy for ring attention where we're sharded on sequence. Um, but there is your point about your point. I in XLA there is which is a compiler for TPUs and GPUs as well. actually. There is decomposition of all reduced. The looped INSUM basically is implemented, and compiler automatically will reduce that unless your all gather is latency bound, or yeah, if your all reduce is too small to do the decomposition. There's some caveats, yeah, but I can share that code as well. Yeah, if anyone's interested. Uh, yeah, should we
Okay.
go to USP? Yeah, should we go to USP now?
Yes.
Okay, so I will please read I don't know how much of it I want to read. So yeah, I guess we all are aware of the continuous chase for longer and longer context lengths, which is what is driving innovation in sequence length optimizations. Um, yeah, there's models which boast 10 million token sequence length, like Gemini 1.0 is saying, and yeah, I personally got interested in this because I was working on a model, a diffusion model that also has 1 million visual tokens. Um, so these breakthroughs underscore imperative are the imperative for generative AI techniques to adaptively handle a larger context length. Sequence parallelism, a technique that partitions input sequences, has emerged as a promising approach for the training or inference of longer sequences. So here's what they say. They bring up this point here. They say this exploration, initial exploration period of 2 years. At the latter of 2023, two landmark works, Deep Speed Ulysses and Ring Attention, mark the maturation of the SP technique. They basically have like not even looking at those weak techniques that Ulysses was referring to. They have started from the baseline of Ulysses and Ring Attention here, and they say Ulysses maintains a constant communication volume when sequence length and compute devices are increased proportionally. This is basically being parroted from that paper, Deep Speed Ulysses, the point that I was earlier bringing up, which actually I just wanted. The reason why I discussed that was because we can see like how that point is kind of obvious point. Yeah. While ring attention hides P2P communication costs introduced by SP through overlapping computation and communication, challenges remain such as the SP parallel degree of the deep speed Ulysses. See, this is not a great statement because here he started off saying, talking about while ring attention hides P2P cost, you would expect that the the next statement would bring up the other side of the while, which would be a drawback of the ring attention. But this
Hmm.
being limited to the attention heads is a drawback of the deep speed Ulysses. Um, so as we already discussed in deep speed Ulysses that the sharding is on heads. So Daniel actually made one of the points about why it's not great is that you're not sharding on sequence, so you may run out of memory still because if you have long sequence length. Another point is that your model, you can only scale as much as your number of heads. So if your number has is like 32, you can't, and if you have a mesh of 64 devices or 128 devices, you're not going to be able to scale on that completely. You will have to do a hybrid parallelism. You're forced to do a hybrid parallelism. Uh, that's an aspect of this. For large scale training, you're limited by your number of heads. And here, the drawback of the ring attention that they mention is the computational efficiency attention degrades due to subdivision of matrix multiplications. This is a not a black and white point as this, as my opinion, at least. We can discuss this again. I'd like to hear your thoughts on that. Um, So in this paper, we delve deeper into the realm of SP. We begin by highlighting that Ulysses and Ring are not mutually exclusive approaches. They can be combined through a hybrid parallel strategy to mitigate their drawbacks. And we discuss the relationship between SP and other parallelism forms data tensor zero, expert, and pipeline parallelism. Most complex among this is the relationship between SP and tensor. Yes, that's highlighted by multiple papers we've seen, async TP and SP, and the deep schedules where these two are frequently combined, and they are exclusive in zones of the layer, in layers of the block, of the transformer. The primary contribution of this, we propose a unified sequence parallel method that integrates speed uses and ring attention. We also systematically analyze the application of SP in conjunction with tensor parallelism 0 and pipeline parallelism as 4D parallelism, and provide a list of best practices to apply SP. So yeah, these two are great. I like the second one personally, very very good, actionable. Just have a couple of feedback for that, but yeah. Uh, I think this just covers this sequence parallelism approaches. This just covers basically the comps used in sequence parallelism, and and the sharding that is the local shapes for the QKV in the attention op. Um, yeah, and here's this diagram is a good summary. As I already explained before, we looked at this Ulysses diagram earlier, right? We see that this all-to-all transforms from the sequence sharding to head sharding within the attention, to compute the attention. And in the ring attention, we have a yeah we do a, I don't know if you're familiar with Jack, so we do a p permute, and yeah, uh, over this ring, and we are sharded on sequence. We do partial calculations of the numerator and the denominator, correct the row-wise scores, max scores, and correct those numerators and denominators. And then at the same time, we kick off getting the results from the previous device in the ring. So that's this ring attention diagram. It's not that great. Actually, I like the diagram that we had in this reading group. Yeah, so that was a summary of that. And then now here they discuss this unified, introduce their method, a hybrid, which essentially just combines these two. It's like it doesn't modify either of them in isolation. Just so we are clear during this, when we go into this presentation, that neither of those two methods, the Ulysses as well as the ring, are modified. They're applied as is. They're combined in a way that they're exclusive to each other. Uh, so they don't interfere. They don't change fundamentally the strategy of those two. They just subdivide the computation into two. You can think of it like that. So SP Ulysses is sensitive to number of attention, as we discussed that. Can someone mute? Yeah. SP Ulysses is sensitive to number of attention heads. Yeah, I think someone has the audio leaked.
I muted them, but I think they just left, so we're good.
Thank you. Yeah, so SP Ulysses is sensitive to number of attention heads. The parallelism degree of deep speed Ulysses cannot exceed the number of attention heads. Consequently, it's not suitable for GQA and MQA scenarios. For instance, Llama 3 8 billion employs grouped query attention with a KV head number of 8, which means that when using deep speed Ulysses, the maximum SP degree is 8. This essentially is actually not just a limitation for GQA and MQA, but like it's a limitation of just the number of heads. And with GQA, you have lesser number of heads. So that's I mean the KV heads at least. So and this Ulysses limits you on both KV. So 2 and KV. So if your KV heads are like in GQA in Llama 3 8B case, it's 8. So that's why the SP degree is you're limited to 8, which is really bad because most people will, for large scale training, will have a number of devices greater than 8. Yeah. Anyone have any thoughts on that? Is that an
Um,
exaggeration?
no, I'm just curious. Like that makes sense what they're saying. Are limited if you're gonna shard on head, then you're limited by the number
Yeah.
of heads. But at the same time, in the
But
actual implementation, they usually do like a repeat or repeat interleave on the KV blocks, so that before you do the mammals with the Q or the K, and then like with the V and whatnot, so that your dimensions actually align. Um, so I'm curious. I mean, I don't know the answer. I'm just like, why can't you do some kind of repeat and then shard? I guess that defeats the purpose of having fewer heads in the first place, like the memory benefits. If you actually
yeah,
duplicate, um,
yeah,
yeah,
yeah. I meant more like, is this the number of heads in practice really a limiting factor? Are people like talking about that? At least in my work, people did like balk at this when this limitation comes out. They say, "Oh, that's bad. I
they
just want to
bulk.
if that." Yeah, yeah,
What I don't know.
yeah,
I don't
yeah.
really quite. You're saying which limitation you're referring to? You're limited your sharding dimension for a sequence parallel by the number of heads. That limitation.
Yeah, 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 yeah.
I mean, this hasn't really, honestly, in the like Torch Titan and stuff. We don't. This isn't implemented. It hasn't come up, so
Yeah.
I haven't really discussed it with anybody. Yeah.
That probably is an answer itself.
Mhm.
Uh, yeah, so SPUing is inefficient in computation and communication. Ring attention segments the QKVO tensors into smaller blocks, which can lead to a decrease in computation efficiency of the fused operator QK transpose, softmax QK transpose multiplied by V. Even if the communication and computation fully overlap, the total execution time lags behind that of deep speed Ulysses. When using a causal math, well, let's discuss that secondly. But this is when which can lead to a decrease in computation efficiency. I I am not sure what they mean exactly by it. I mean, it's surely, yeah, you are doing smaller computation, so you do reduce the computation efficiency. But I presume you even the chunks of computation that you do, you fully use your VMEM and your registers, your MXUs. What at least I mean, are like this isn't this same point? Can it not be made for flash attention? Right? If we purely just look at it from decomposing into smaller blocks, but but we still but we still keep the flash block sizes. We align the flash block sizes to the MXUs, how big the MXUs can hold, what blocks of matmos or computations they can do, right? For like TPU, for example, we normally keep for old V5 generation, which has a 128 MX can do a 128 by 128 multiplication. So we have the flash block size to set to that. And for newer generation, we have slightly bigger. But is this a valid point, like for ring attention?
Are you saying what you said as a valid point, or what this paper, this like two sentences
What
right
this
here?
paper saying? This
Yeah,
paper
I
saying.
think
I mean,
I can give you my take on it. I think it's kind of like an obvious point what they're saying. It's like of course with Ulysses where you have the access to the full sequence length and you can compute like QK transpose in one shot without any comms, at least just for one head. I mean, then like yeah, of course that's going to be faster. And so if you're in a situation where you don't with the full sequence length and just sharding on the head dimension, then yeah, of course it'll be faster because you're not doing any comms. But the whole point of ring attention is like yeah, maybe it's a memory optimization technique. It's like reducing
yeah,
peak memory and allowing you to expand your sequence length. So it's like, yes,
yeah,
it will be slower. You're decomposing your computation, smaller, less efficient mammals, but you can actually expand your sequence length, quote unquote, indefinitely, even if your execution time is not infinite. So it's not really like a one-to-one comparison. Like one can scale up
yeah.
supposedly infinitely, and one is limited and will hit ooms. So
Right.
there's a trade-off basically.
And like, isn't this the same point? Like, you can make. I mean, you would avoid breaking down this compute. Just it's the same point I think I'm making the same point as you. Is like if you have a smaller sequence length, you wouldn't even want to break down this computation so much.
Yeah.
Yeah. So I
That
mean,
you
this
wouldn't
is
even
this.
use ring attention. Yeah.
Yeah. Yeah. So I mean, this is like the point that I mean, you can say this about flash attention too, right? If you have a very small attention, do you need would you, your dot product attention may perform the same as flash?
hmm Well, I don't know about that. Because just the
I've
HBM
seen that.
accesses will be lower. So, I mean,
What
it might be a
HTML?
small difference.
Hmm.
I don't know actually. There could be maybe there's some threshold where it's small enough that like somehow there's additional overhead
Yeah.
through the flash attention algorithm, but I don't think so. I mean, it's just like fewer HBM accesses at the end of the day, and so it should be strictly faster. But I don't know.
Yeah.
I could be wrong on that.
In max text, we do selectively use it.
Really?
Yes.
On
Yeah.
what
Because
condition?
like I said, I have to look at exact condition, but basically the gist of it is that in some computation blocks is when it's so small, you don't need it.
Hmm. Interesting. Okay.
And add to actually some overheads of the flash attention, the kernel overheads.
You should
Yeah,
ask whoever added that conditioning and like let me know. I'm just curious.
yeah. I had asked,
So
but I forgot.
I don't think we
I
do
would.
that. Yeah. Okay.
Anyways, continuing with this, I think yeah. So this is a point that's like kind of in a vacuum looks good, but actually it's a moot point because you wouldn't be reading this paper if you didn't have the problem of memory. Yeah. Secondly, when using a causal mask that has not been addressed, the DS ring has a load unbalancing issue. Uh, yeah, this is true. I think this was discussed earlier as well. Um, in ring attention, we assume that we are dividing the computation equally on the ring, but with the causal mask, that's not the case, right? But no,
hmm
most people get around this by doing striping, and this is I think this is a problem for flash attention as well, right? Where and you do some sort of striping to rearrange rearrange basically, and then send those divide make the computation division equal.
How is striping different than what is shown in the diagram below?
Yeah, it is the same.
It's the same.
Exactly, it's the
Okay.
same. Yeah, it is the same. Yeah, this is they call it whatever they call it, but I think we call it striping in max text.
Load balance partition. Yeah, I actually have a question about this. Um, so I think it's interesting they didn't, at least to my recollection, didn't mention this uh, imbalance in the ring attention paper. Maybe they did. It's been a while since I read it, but I think that's interesting drawback. But it's well, not drawback, but like side effect. But basically, when you move these things around, or you like say GPU zero is responsible for like 0 and 1, does it change? I'm just thinking about how this works with like positional encodings. Like if you have a naive positional encoding that's just like an embedding table, um, then sure, it makes sense like an absolute position basically, and so you could move them around. That information is not lost. But if you're using like rope and uh, which I believe has some kind of like relative distance involved in the formula,
Yeah,
if
yeah, yeah, that's right.
if you kind of just have like zero, like you have tokens 0 and 1, and then 15 and 16 on the same device, um, I'm just a
Is
little
it
bit
relative?
fuzzy on how this would work.
Does rope have relative distance or the angle between the two tokens?
I think it uses the relative distance as part of the like rotations that it
Rope.
performs. I can't. I would. Someone double check me on this though. I'm like halfway through that Eleuther rope blog post, and my tab has been
Yeah.
open for like months. I need to finish it. Um, yeah,
Yeah, that's interesting. Yeah, I hadn't thought of that
they
actually.
they mention it in the paper, but I just wasn't clear still. Like if you just scroll, I think somewhere it says rope, and
There.
I was just unclear how to address it.
This in this paper?
Yeah,
Let's see where it
yeah,
is.
right here.
Yeah. There's no encoding
Positional
only.
encodings only involve analyze operations. The same reordering operation also needs to be applied to the positional encoding parameters of the model. Since the operation is applied to the model's input token sequence, which is an integer vector of length bs times length, The additional overhead for load balancers. And see, this is all they said, and I'm still just not. Maybe if
Yeah, this
somebody
implies
else,
redo the rope.
it kind of sounds like that's what they're
Does it?
saying, yeah. But doesn't that aren't you like losing the actual? I mean, clearly you must not be, but in my current understanding, it seems like you'd be losing the actual original ordering of the
Yeah, yeah,
words.
yeah. You lose
Um,
the purpose in the rope for the attention, right? You're doing the rope for the attention to have that um,
I guess. Hold on. I guess
relate.
maybe do you compute rope embeddings and apply them before you do the reordering, and then you reorder, and then that information is already there? Or is rope no rope is part of the actual QK matmul itself, right?
Yeah, no,
So
be part of the after the projection.
yeah, they I need to. I don't want to here. I'm gonna open this in another window really quick so you can still see in the recording your screen, but look at this. I really need to understand rope better.
So here I have some stored. So here we apply rope to the projections right after the projection. Yeah.
Let me see something really quick. You can keep going if you want. I'm just gonna pull up this code
Yeah.
and check something.
Just, yeah, just interrupt when you found
Mhm.
something. But anyways, so yeah, ring attention has a drawback of that you need your computation to be perfectly balanced. When you're using a causal mask, you have a triangular matrix and you don't have it perfectly balanced. If you just divide it as it is. So you have to segment your groups, and that technique is called striping. We will later see it. Yeah, in this paper, they still have to use it because, as I mentioned, this is just a combining two techniques independently. Uh, yeah, so let's just dive into the algorithm now. We can we will find that how they are combining. So as shown in algorithm 1, SP ring and SP Ulysses are organized in a hybrid parallel manner named USP attention to work together in partitioning the sequence dimension. The SP process group is segmented into two orthogonal process group sets, set of SP ring process groups and set of SP Ulysses process groups. For a more intuitive understanding, an SP process group can be viewed as a 2D mesh. SP ring operates across each column of the mesh, while SP Ulysses runs across each row. For example, a process group containing 8 processes could be viewed as 2 by 4, where SP Ulysses process group Ulysses PG of size 2 and an SP ring process group is Ulysses PG of size 4. This is the same as how data and tensor parallelism process groups are partitioned. This puts the USP attention include the segment of QK and V tensors after being partitioned along the sequence dimension, and the output is tensor O shard. The size of tensor segment is batch size as sequence shard, which is sequence length divided by number of devices in the sequence ranks. Uh, head size, uh, well, that should be wrong. I think this should be, they meant to say 8C here, should be the head
Mhm.
count. And then the last dimension is the uh, head dimension. Note when using MAQ, I think this is a typo. They meant MQA here, multi-core attention. The shape of the HC head count for the K and the V tensor segments differs from that of the Q tensor. Yes, like we mentioned, KV has lesser number of heads compared to the Q because of grouping. During forward propagations, scatter IDX axis is set to 1 and gather IDX axis is set to 2. All 4D merges the dimension L and partitions the dimension head count of the tensors QKV and transforming them into head count by number of devices. This is a little bit confusing because this is not the original N. It should be the Ulysses degree here. This is another typo, I would say.
Wait, what? What
Batch
is this?
size,
What is it in then?
it's the Ulysses degree.
Oh, okay.
Yeah, it's not this n and this n is not the same n. If it were,
Ah,
then we are just doing
God.
Ulysses. Yeah, yeah, yeah. I kind of I sent the author a message. He wasn't too pleased. Yeah.
Oh man.
Yeah. A lot of people actually had yeah, he put up a post in the Chinese Reddit, and a lot of people had like nitpicked. Yeah, he was already.
They
Yeah,
picked on him?
yeah.
Oh
Yeah.
man. So I'm a little, do you want to talk about this algorithm first? I have a couple questions on it.
I was just gonna read it out, and then I was gonna talk about it.
Okay.
Yeah. They also partitioned the O tensor along the L dimension and merged the head HC dimension. During the backward propagation, the scatter IDX is set to 2, gather IDX is set to 1. So here, let's talk about this algorithm now. Do you have any question before we dive into it, or you just wanted us to go into it?
Let's talk about it and then I'll ask a question.
All right. So how does this work is that when you enter this, let's say this USP block or whatever, USP attention function, we assume that the inputs are QKV projections and they are sharded on sequence at this point. They enter with their sequence dimension being sharded on total number of devices, let's say n. Uh, call it a sequence parallelism degree. Yeah. So be absolutely clear, when the inputs to this attention function, USP attention, is sharded on sequence and nothing else. Well, you can have tensor parallelism if you're sharding. So, but let's just say for simplicity purposes, it's sharded only on sequences, and that's the total number of devices. So the first step here, here we see the in this algorithm, steps 2, 3, and 4 is basically to transition from pure sequence parallelism to Ulysses sequence parallelism. If you remember, in the Ulysses sequence parallelism, we do an all-to-all to go from sequence sharding to head sharding, right? But the only difference here is because this is hybrid parallelism, we only do we segment the original n devices into a 2D mesh of Ulysses and ring, where Ulysses is the outer dimension and ring is the inner. So you can think of Ulysses as the row and the ring as the column. That's what we segment. If we originally had 8 devices along which your sequence was sharded, the QKV sequences were sharded on these 8 devices, you and then if let's say if you had Ulysses degree of 2 and ring degree of 4, then you are having a 2D mesh of 2 by 4, which is equal to the sequence original sequence ranks, and so you convert your mesh from a 1D mesh of sequence to 2D mesh of Ulysses by ring, and then you do all to all where you're performing this all to all within the Ulysses degree, within only the devices in the Ulysses degree. So that's the key point here. So you do an all to all only within the Ulysses degree. So what in this all to all does is within the Ulysses degree of devices, which is our 2 here, 2 devices from which is 2 groups actually. I misspoke there. 2 groups from the original 8 devices. We divide it into 2 groups of Ulysses. Within these individual groups, we do an all to all. So what happens is we do a scatter and a gather. We scatter along the head dimension. If you remember the deep speed Ulysses that we covered at the beginning, where we talked that we go from sequence sharding to head sharding through an all to all, where we scatter on a head and gather on sequence. So this does that. Only difference being that it does from a subgroups of the original devices, which these subgroups are just Ulysses groups. That's the main point here in this 2, 3, and 4, which is basically the Ulysses sequence parallelism part of it. And then number 5 is just performing ring attention within the subgroups. Because within the subgroups, they're all sharded on sequence still. So you have 2D sharding. they have the same heads, but they together collectively form a sequence sharding. They are sequence sharded, but they also have their heads are replicated within the Ulysses group. That's my point. Is that clear? I think I have a diagram as well, if that will make better sense. So let's see
Oh
here,
wow.
right? This yeah, maybe it's more confusing. I don't know. Uh, if these were originally the 8 devices that we had, and when we do an all-to-all, we gather on the sequence ranks within the SPTP. So I had divided into 2 Ulysses groups here, as you can see, and the boundary colors represent the ring ranks, and the fill colors of these rectangles represent the Ulysses. So we can see that there's 8 devices, 2 groups of Ulysses, and within those there's 4 ring ranks. And originally they're all equally divided on these 8 devices. Then we have all to all, where we gather on sequences and shard by heads, and then we have 2 rings basically, or 4. Within these 2 rings, if you see the local shape, we have the same heads on each device, but the sequence is sharded on each device. And then we have the head dim, and we do the same ring ascension computation where we overlap the yeah, I think I mentioned this plenty of times today. Essence of the ring computation, where we have to correct our numerator, pass on the numerator and the denominator of the attention up. And then finally, we have another all-to-all to go back to purely shard by sequence globally. Yeah. I know it's the wording in the algorithm and the paper makes it a little confusing because they use the n notation twice. The
Hmm.
n means different. Yeah.
I think I understand. Can I just summarize my understanding really quick, just to confirm my understanding?
Yeah.
So for me, it's easier to visualize just as a rectangle, like the mesh basically. So let's say we have the rows or the Ulysses dimension, right? Say we have 2 rows, and then we have four
Yes.
columns. So 4 columns,
Yeah.
which is the ring group.
Yep.
And so along the Ulysses dimension, the first three are, if we do the all to all 4D to have the full sequence length for each Ulysses rank, but only a certain shard of the head count. But that full sequence length for that Ulysses rank will be sharded across that that ring group
Ring.
for that given
Yes.
Ulysses rank. And then
Exactly.
it will do the regular load balanced ring attention algorithm across, like horizontally, across that ring attention group for that Ulysses rank, and then like rotating the key K and V around, and then at the end we have the all to all 4D to go back. Instead of sharding along the head, we are back to sharding along sequence for the output activation and sending it to the next layer.
Yeah. Exactly. We at the end we go back to 1D mesh.
1D sharding. Okay.
Yeah.
That's interesting. I never
Yeah.
thought about this. Is like a really clever idea, actually. I didn't.
Uh,
How do you actually implement this though with a mesh that's only?
I
I guess
have
I
it
guess you can have like you can have multiple meshes or like views on meshes to have like a temporary 2D like view of a mesh for these to have like these specific groups, and then the subsequent layer you can just go back to like a 1D.
here's a implementation that I just did for last week.
Oh, cool.
It's yeah. So one thing here is that because I implemented this for a diffusion model, we don't have we are using full mask, so I don't have the load balancing problem. That simplifies a lot of things. Um,
Say
yeah,
that again. Why don't you have the load balancing problem?
because I don't have, I'm using full mask.
Oh, there's no causal masking, you mean?
Yeah, there's no causal mask.
Oh, why? So I guess in a diffusion model, there's no or like there's no like causality between the tokens. These tokens are just like parts of an image or something. Is that it? So the order doesn't
Yes, that
matter. Okay.
uh, actually, they do. They are in time dimension as well. So, but yeah,
Okay. But within,
but
but with.
so sequence length is constructed. If you're curious, I can summarize this. So if when we have a video, we break it down, and then the sequence length is basically initially we down projected into latent space.
Hmm.
The we each frame is an image, you can think of it, and we have stack of frames. We down project the all three dimensions, the time, head, height, and width into, and we upscale the channels uh, to get to embed more information.
Hmm.
Uh, and and then when we break up this into patches of through we have a use a convolution kernel to break it into a patches of
Hmm.
across. We basically merge the three dimensions of time, height, and width, and only keep that, and the final dimension being the channel dimension. Expand we expanded to the head, the model dimension, basically.
I
So
see.
that patch dimension, the so it's so this is just a, yeah, that's why it doesn't matter, because we are collapsing that whole thing into one
Interesting.
sequence.
Okay.
The sequence length is like your factor of latent compression or time, height, width, and whatever your patching kernel dimensions were as well. So it's a multiplication of all of those three.
That's interesting. Is that technique based on any paper, or is it just like a
Yeah,
practicality? Like a,
this is this is like a very, it's been common. I think who introduced it? There was a paper called MMIDT. Yeah, diffusion transformers, and I think it was came after. I don't know which video model brought it, but basically, if you're aware of any video models these days, some of these Chinese models, the
hmm.
Van, Fling, and yeah, they all use this. Yeah,
Hmm.
Lightrix. Yeah.
Okay.
So
Cool.
that's, yeah, that simplifies a lot. That's basically from my implementation. I don't need to worry about yeah, the striping, which actually I heard from my colleagues it can be pretty hard. Yeah. Anyways, so as I say, if you we can look at this implementation quickly. Uh, we get the QKV, which is sharded along the sequence on globally at this point. This is, you can think of this equivalent to the USP attention function that they said. And then we have the flash. Well, yeah. Also, yeah, you do use flash attention with this. You can use ring attention in combination with flash attention. Uh, I don't know if, I think because I mentioned this because in the paper they mentioned that this needs a new kernel, right? But the complexity of this kernel is pretty just a lot less because it's a nested kernel you build on flash attention.
Hmm.
Um, yeah, and so here is the basically I get the shape of the global sequence. The in the I get the number of ranks in the global sequence sharding. This line does that, and then yeah, there's some padding and stuff that you do for flash attention, and basically redundant line. Yeah. And then, yeah, I check whether it's divisible because we have to divide this 1D mesh into 2D. So I check whether it's divisible with USP degree or not. Yeah. And then you get your ring degree from, derive the ring degree from the USP degree. And then you recreate a new mesh for the 2D. You recreate a new 2D mesh and you reshape your mesh to that new mesh. Basically, these three lines in this Jax will do that. Uh, and then yeah, this is just inputs to the yeah, this is this all to all basically here. is what is the all-to-all that we see in this USP algorithm. So as you can see, I perform the all-to-all on the USP ranks, and I have my gather axis and my gather axis and the reduce axis uh, specified here. So this gather axis here is the sequence axis. This reduce axis, the split axis, is the uh, is the head axis. Head count, so number of heads, not the head dim. Yeah, so that this all-to-all is that's basically what this all-to-all looks like it implemented. Not that complicated. Uh, and then yeah, that's it actually. I invoke this. Yeah, I have I specify the shardings or how we are sharding. So you can see actually this is a slightly interesting part here is that we have the USP and the ring combining to form the sequence dimension as the initial spec, because before I do the all to all, my I have my the GPUs or the devices that are in the way and that if we consider the group of devices as a physical axis and my logical axis being the dimension in my tensor, the sequence tensor is mapped over this USP and ring when I did the reshape. Uh, but then when I perform this all to all, my output is going to come out differently, where I have the ring, my sequence sharded on ring, and I have again, this is slightly different from the algorithm, is that because I already use tensor parallelism as well, we support it. So actually, it's gonna my heads will be sharded on both USP degree and tensor. That's why. So this is the input sharding and this is output sharding.
Wait, sorry. Can you say, wait, how can they be sharded on two different things for tensor and USP, the heads?
I haven't. I think if it should work, but so because originally I already was sharding my heads on tensor.
Hmm.
That's that's why
I thought
at
they
this
said in the
initial.
paper that USP head sharding is like incompatible with tensor parallelism for that
Yeah,
reason.
yeah. So actually, this should be set to one. When I so this is like a program. I didn't want to change the code so much. So instead of completely ignoring the tensor and like it gets complicated to map the sharding, so I have a validation logic to ensure that tensor is only set to one.
I see. Okay, good.
Yeah, but the main point here is being that originally this is the sequence, and then we get the sequence and the head. Don't get confused by the ordering because there's a rearrangement that happens. We go from sequence head, uh, we go from head sequence to sequence head in the shape.
Hmm.
Yeah,
What
and
all
that's
right.
about it.
In shard map, I'm just
I just want to wrap it up here. Is that the final point here is that this is the last tab where we do globally sharding. So you go back to the original sequence sharding.
mhm.
Yeah.
Awesome. This is
All
a
right.
nice, this is a very clean implementation. So I just have a question. I'm not as familiar with the JAX API. So in that line 324, there's like shard map. So there's your kernel that has like the alt-alls and stuff, right? Um,
Yeah.
Logical mesh. And then are the in-specs, there's three of them. Is that for QK and V, or what are those three associate?
Yeah.
Like, what
Yeah.
are those?
Those are the sharding specifications for the QKV.
Okay, and that's for the input shardings, and then our output shardings, you just have one, and is that what replicated for everything, or like how is it? Um,
That's the output from the ring attention.
okay, I guess I'm a little confused why there's three input specs but only one output spec.
Because because the input for the attention is three
Oh, and
tensors.
there's just one output. Okay, got it. What is And then can you go up a little bit on on the all to all the tiled equals true? What does that do exactly?
Yeah, that's a. I have to ask the person who wrote this. this all-to-all API. But from my understanding is it shouldn't do that. But we can I can show you what it quickly looks like.
Hmm.
It's like I didn't truly get that. It basically is some sort of the implementation of the all-to-all uh,
Hmm.
and
Yeah.
how it does it. That it chunks it up.
Yeah, see, I was just confused, like tiled, like dividing along split axis and then concatenating along the concave axis. What that sounds like the whole point of what the USP does, where it's like splitting along, like we're just like changing the sharding dimension, like we're splitting along one dimension and then gathering along the other. So I guess
Yeah,
what would happen if we set this to false? Would it just
it would do the same. I think this is just like into chunks, splitting it into chunks of
No,
doing that.
I think it's a communication optimization. Just
Yeah, exactly.
do bucketed communication instead of sending the tensor as a whole. Yeah.
Exactly,
I see.
exactly. Buffering. Yeah. That's my understanding. I have to confirm it, but yeah, it's by default it's false. So it might not be great for performance.
Oh yeah, interesting.
But I plan to just ask that question to the author.
Is sorry, does anybody else have any questions? I feel like I'm like dominating with the with the comments.
I'm good at least.
Okay, anybody else please chime in, George or Gothos or Luigi. Don't be shy. But in the meantime, I'll ask the ring attention implementation you referenced in your code there. Is that something that's like natively provided by Jax, or is that like an implementation specific to Max Diffusion, or like where are you getting that from?
Yeah, it's native. It's in Jax. The author How wrote it in Jax.
Oh, I see. And so is it? So it's actually part of the library.
Yeah.
Wow, that's awesome.
Yeah, but it's not actually. It's not in my next task. Actually, is to integrate it into splash attention, which is sparse splash attention,
Hmm.
and see, because that I think is not is slightly suboptimal right now, because just uses naive flash attention too. So
What does it mean for Flash Engine to be sparse?
it's just to flash attention for sparse metmals.
Oh,
That's understand, yeah.
is that
So
for? Okay, never mind. Yeah, I guess that makes sense.
yeah, I can send you the code if you want to look at it.
Okay.
Yeah,
Cool.
but it's not possible right now to integrate because it doesn't support like KV sharding. So that's the problem.
Hmm.
Yeah. Uh, yeah. Anyway, so this was the gist of it. I think. Yeah, and I only this the backward pass is you have the conjugates of these comps. Uh, yeah, you would like do the reverse of it. And then yeah, let's go into the cost. Actually, firstly, does anybody have app? I hope someone chimes in here on what they think of this paper's optimization over ring and deep speed. Like, are they sold on it? What do you guys think about that? Are you guys sold on trying out this for long sequence length, or what would you consider before trying using this over ring or purely Ulysses?
I mean, I think it's very interesting. It seems clever. I would consult. I actually want to show this to some of the people in the distributed team and get their thoughts on it because
Yeah,
they're
yeah,
experts in this domain.
yeah. Please share in the chat and yeah, about
Hmm.
what they tell you as well.
Okay.
This because I'm very curious. I asked opinions from other people as well in my in the in our in DeepMind, and they in their opinion, I asked the ring attention author actually. as well. In addition, he is quite supportive of this. I'm not sure how much he has deeply looked at this implementation,
Hmm.
but the communications is overall is the same as the ring. The key point that he mentioned is that we have less of the, how to say, we have less uh, kernel launches compared to ring attention, right? So he thinks that that is a, you can you have another dimension of balancing your your trade-offs, so to say,
Hmm.
uh, where you can like just like micro calculate this stuff to like say the optimal ratio of USP to ring, where you have your kernel launch overhead is worth the overlapping. Yeah. Also depends on the implementation. Some people that I talked to in when they told me about the ring attention, they also factor in the time to transfer from HBM to VMEM, because in the implementation of ring attention kernel, this will be determine how good of a pipelining job you can do.
Hmm.
So this, perhaps if you calculate it, factor in that cost as well, this can be better. But on the overall side, if you have long sequence length, I think ring attention outweighs Ulysses. So you would have a always. I feel like your ratio, and also more importantly is this paper. If, I don't know if you have time to go over all of the tips and stuff, but this paper essentially gave uh, summarized the points earlier. Actually, the tips are not that much of new information, but they have used, and I don't know what is this. Does anyone know what L20 is?
It's a type of GPU.
Is that a like a powerful GPU, or is that a consumer grade GPU?
I don't think it's like mid tier. I think if I'm
I
I think
see.
it's Ada
It's a
family, so it's around Hopper.
Oh, is it? That's not that bad then.
hmm
It's like consumer version of Hopper essentially.
I see.
Ada family as a whole, if I'm correct about L20 being Ada.
I see. Does is it have like the same like 919 flops or for BF16, or is it like similar or like less slightly worse?
Oh, I don't know. I'm pretty sure it's much worse than Hopper because it's um, consumer grade. But something that I think if you Google it right now, I can see it. But I don't know how it compares to what you are saying.
Yeah, my point was that you cannot determine this the ratio of Ulysses to ring just by looking at your computation size. Then you have to look at your computation time and communication time, which will which is effectively influenced by the compute to interconnect ratio. And my bigger point here is that uh, I at least know the A100 is at least 2 generations old now, right? We have
hmm
B Blackwell and we have Hopper. So, and that is a and also this, I assume this NVLink is a lesser speed compared to the previous ones, with the ones for the Blackwell
hmm
support. So your decision making of the ratio for USP to ring will drastically change based on this compute to ICI ratio. And my understanding is that that ratio has gotten worse in newer generations. At least on TPU side, it has gotten quite worse. So as it gets worse, you should favor ring attention more, because is my understanding, because you have your computation gets faster in relatively to your communication, so you benefit more from overlapping, breaking up your computation, because you don't want to do you lose more you lose percentage wise, you are losing more by having to wait for longer time in relation to the compute time.
Hang
because it
on.
all to all was blocking.
Um, But okay, so on these later generations, though, the global memory also goes up a lot. Isn't it like 192 gigs or something with the latest CPU? So ring attention being primarily a peak memory reduction optimization, isn't there
That's
like
true.
regardless of the comms, isn't it there kind of a less need for it? And it does, as the authors mentioned, that even if you do fully overlap, the actual execution time will just be slower, even if the execution time scales linearly due to the overlap. It will still be
Right.
slower.
Right. Yes. Yes. But yeah, I mean, if we discuss this in the context of 1 million sequence length,
hmm And so, what was your thesis exactly? Why ring attention would be preferred?
assuming that you already are at a situation where you must reduce your activation memory,
hmm
I think if you're at that point, then I think if you're implementing USP, you favor ring degree based on the if you're based on the ratio of your. I think I was trying to derive a formula of this ring to Ulysses ratio, and I think when I haven't derived it fully yet, but from what from where I got to, I can see that is relevant is relation to the is proportional to the compute to ICI ratio. So if you have faster compute in relation to communication, and given that activation memory already is a problem, so then you would want to do this. You would want to favor ring degree over USP degree. Is my point. I don't know if anyone has any opinion on that. I would
I'm
have
a
hoped
little
that
on this
you
table.
would.
I don't know. Maybe I'm just slow today, but I'm a little confused. They're saying it's for throughput of SP unified. Okay. But then it shows Ulysses degree, and then it shows iterations per second for basic versus load balanced ring attention. Um, oh, I see what they're. Okay, I see what they're saying. Never mind. I understand the table now. Okay.
They're talking about the iteration
hmm
of the ring. This is comparing the load balance ring to the basic ring.
Yeah.
Yeah, that's so that's my opinion. Anyway, they use 64K here sequence length as well to compare. But yeah, I wonder if anyone uses this in production. They did, is this from ByteDance authors? Not sure if they have used it. Oh, actually, yeah. I did come across a model that mentioned this that they use this 1 million sequence length, and the reason that they mentioned that they use this versus just using pure ring is because of hybrid mesh. I mean, their physical mesh where they have like not heterogeneous communication bandwidth basically in their mesh.
hmm
So like ICI DCN bandwidth.
Sorry, I have a question kind of not related to this exact thing, but when we do, so we're doing at the end of the algorithm, we do alt all 4D again to return back to the original 1D sharding along the sequence dimension, but um, and that's not over the 2D logical mesh, but just like a 1D mesh of all the devices, right? So what is like the
Yeah.
parallelism for the subsequent layer? Like, what is the FFN? How is it parallelized?
It's not parallelized. I mean, it's parallelized over sequence because you go back to
And
sequence.
so it's just like, okay, that's just, I mean, that's not, I don't see that like with just like purely shard over the sequence dimension for FFN without sharding on,
Model
like
DIM.
with not doing TP and SP, like that form, like from the reducing activation recomputation paper.
Yeah.
It just seems odd. Like, I mean, wouldn't they aren't saying like, is there anything in this paper where they say how it's composed with like actual parallelisms, like if I'm using TP and SP on my FFNs or
So
things of that nature?
what they're saying is they don't mention it like in regards to FFN.
They talk a lot about TP here. I don't know. Maybe I'll.
Yeah, but from what I did in my implementation is I just go back to combination of TP and SP.
Yeah, that would make sense.
Yeah.
Because the FFN can be
So I
parallelized. Yeah. Okay.
right. So here in this sharding, right? You see I have the tensor FSDP. Yeah, I just go back to the yeah. I have a bug here, which is I need to ignore the tensor in the original. But yeah, I just go back to the T- TPN. That should be what it should go to. Yep.
Okay, that makes sense. That makes sense. Cool.
Yeah. Yeah, but if you're curious, for my case, I have 40 heads, well, and a head dimension of 128, so 120 model dimension, and 80,000 sequence length. Uh, I originally had the all gather way, actually, right? The all gather way, and that performs slightly better than this than than doing ring and
Mm.
doing USB. I have 8 devices. I did a 2x4 and a pure 8 of ring, and did the 8 sequence sharding without the ring, and yeah, that and KV being replicated. So KV replicated Q sequence sharding did work better. Yeah, and TPUs actually this has even less value, I think, because we TPUs are sequential devices, so there isn't a concept of heterogeneous bandwidth.
Mm. I'll read through these tips later. They seem to be kind of addressing the questions I was asking about, like composability with like pipeline parallel or TP and
True.
SP and so on. Interesting. Cool. Yeah. I got a lot out of this. This was great. So I appreciate the presentation. I would definitely want to show this to some PyTorch folks on the distributed team. We have a reading group for distributed papers as well, so maybe I'll share this.
Yeah. And please share any discussion that comes out of that in the chat.
Yeah. Cool. All right. Any last minute questions for Cool KP?
I need to change my like you
Why?
manual VM. Yeah, professional.
Oh, it's important, to put cool. That way people know. They might not know otherwise. You got to be clear about that. Um,
I was
huh?
yeah, I was using Discord for reading groups earlier. Yeah, yeah, for ML reading groups at least. Yeah,
All
cool KP was
right.
more.
Well, I will stop the recording now.